What we've seen so far is the complete input that must be given to a planner. Now we will turn to the output of the planner, which is of course a plan. And a plan is a sequence of actions A1 through AK. We're using the pi symbol here to denote the plan, and the sequence consists first of the action A1, then of the action A2, and so on until we reach the action AK, and K must be greater or equal to 0, so the plan can be empty and contain no actions. The length of a plan then is simply the number of actions it contains, so it is K, where K is 0 or more actions. Given this definition of plans, there's a number of things we can do with those plans. For example, we can concatenate plans. That means if we're given a plan that consists of actions A1 through AK and another plan consisting of A'1 through A'j, then we can define the concatenation of those two plans as simply the sequence of actions consisting of first all those actions from the first plan and then all those actions from the second plan. We can also extend our state transition function as follows. We can define a state transition function for a state and a plan by defining that it is the state from which we start if our plan was empty. So if there were no actions in the plan, we simply remain in the same state. But if there were actions in the plan, so k was greater than 0, then what we do is we first execute the first action. That gives us a new state. And then what we do, we apply the state transition function recursively to the remainder of our plan. For this to be well defined, of course, our action A1, the first action in our plan, must be applicable in the state in which we're trying to apply the plan. In any other case, the state transition function applied to the state and the plan is undefined. So the most important thing to remember here is we define plans simply as sequences of actions. Of course, there are more complex types of plans, but this is what we're looking at here now. The output of a planner is a plan, but of course, not every plan is a solution to a planning problem. And here is how we can define what constitutes a solution. We are given a planning problem consisting of a state transition system or a set of operators, an initial state, and a goal description. Then we can say that a plan, pi, is a solution for a planning problem, for this planning problem that we're given here, if the state transition function applied to the initial state of the planning problem and the plan that we're trying to execute in that problem gives us a new state, and that state satisfies the goal. So a plan is a solution if the execution of the plan leads us to a state in which the goal is satisfied. Since there may be many plans that are solutions for planning problems, we want to distinguish those, and we can do that by defining some properties of these solution plans. So we can say that a solution is redundant if there is a proper subsequence of this plan that is also a solution for P. So if we can take our plan pi, remove some of the actions, and still have a solution plan, then we call the original plan redundant. And we can say that a plan pi is minimal if no other solution for our planning problems contains fewer actions. So it is minimal if it has the minimal number of actions. Now, all the definitions you've seen so far apply to classical planning. But in fact, there are variations of what is exactly classical planning. Most of what we've seen so far is the strips representation. Here I want to give you a quick overview what other flavors of classical representations exist. The simplest representation is the propositional representation. In the propositional representation, a world state is described by a set of propositions. So a proposition is a simple symbol. It does not contain any internal structure. In the strips representation, in a state we had first order atoms, ground atoms to be more specific, and these relate objects to each other. In the propositional representation, there are only proposition symbols. Actions in the propositional representation consist of preconditions, postconditions to be added and to be removed. The first thing to note here is that there are only actions. There are no operators because we don't have parameters, and that's because we have symbols that have no objects. They relate to each other. So there's no variables, which means everything is ground, everything is an action. Then we have precondition propositions, which means we don't have positive and negative propositions in the preconditions. Only positive propositions exist in this simple representation. And then we have negative and positive effects as before. These are symbols. not ground atoms. And I've also mentioned they are often called the add list and the delete list to be removed. The strips representation then is simply the same, but instead of propositions, we're dealing with first-order literals in most cases. Specifically, this means the preconditions of an operator can be positive or negative. The final variant is the state variable representation, where a state consists of a set of state variables. A state variable is simply a variable that must have a value. It's usually described by a function. So for example, we could have a function that describes the location of the robot, rlog, that takes a robot as an argument and tells us where that robot is at location L. The advantage of this representation is that it represents the functional property of this. The robot can only be at one location at any one time. So in the strips representation, at least in theory, you can have several assertions of where the robot might be. In the state variable representation, the functional property, namely that the robot can only be at one location at a time, is exploited. Actions in this representation are simply described by sets of preconditions that look like expressions like this, and assignments of new values to these state variables like this one. So what you need to remember here is that there are different flavors of the classical representation. There's not just the strips representation we've looked at. There's also these other two. But, and this is the important point, these representations can be translated into each other. So essentially they're all equivalent in terms of expressiveness. There's nothing that you can say in one of these three representations that you can't say in the other.